everyone, this is my video editorial for Codeforces round 955. There are going to be hints and I will be explaining my thought process behind all the solutions, so hopefully you'll have a better idea on how to solve the problems. Don't be afraid to pause after a hint and think more about a problem. In problem A, we're given the score of a game between two teams at a certain point in time, then the score of the game later on. We want to know if it was possible for the game to never be tied between these 2 points. For example, if the score is 3-5 at our first point in time, then 4-7 at our second point in time, this is possible without the score ever being tied. However, the score cannot go from 3-5 to 6-5 without the score never being tied. Our claim is the game has to be tied at some point if the winning team changes. This is because the game has to be tied before one team overtakes the other. However, why is it possible for the game to not have a tie if the lead never changes? We can always increment the larger variable until we get to the max, then increment the lower variable like shown on the screen. And now let's code this up. The code is pretty simple. We check the two possible winning cases. Either the first team is always winning, the second team is always winning. Otherwise, the game has to be tied at some point. The code is pretty short. In problem B, given two integers, x and y, and we perform this operation k times. We increase x by 1, and then while x is divisible by y, we divide it by y. Our goal is to find the value of x after k operations. On our first operation, we add 1 to x and get x equals 14. Then we add 1 to 14 and get 15. However, 15 is divisible by 3, so we set x equal to 5. Then we add 1 again to get 6, and then divide by y again to get 2. Then we add 1 and get 3, divide by 3 and get 1. So on our final operation, we add to get 2. So after 5 operations, x is equal to 2. So how can we approach this problem? Our first hint is to pay attention to when we're doing the division operation. For example, if x equals 13 and y equals 19, we will do addition 6 times in a row before doing division. So we can look at the difference between y and x mod y to see how many times we do addition before another division. Our next hint is that we don't need a lot of divisions to get x down to 1. But what happens when we get down to 1? Let's visualize what happens for y equals 4. As we can see, a cycle happens where we get up to 3, and then on the next operation we go back to 1 after the division. So there's a cycle of size 3, and now let's code up the ideas we got. First, we brute force until x equals 1, and we know this while will only iterate around log x times, so we don't need to worry about the time limit. Then we can check how many more additions we have to do before the next division. If k is less than this number, our answer is x plus k, as we can just do k additions to x without having to do division. In the other case, we have enough operations to get to the next division. We add these to x and then subtract these from k, and while x is divisible by y, we keep on dividing and repeating the while loop. Finally, we saw earlier there's a cycle of y minus 1 once we reach y. Using modulo, we can print where we are at the end of the k operations, and that's it for problem B. In problem C, we're given a deck of n cards with a number written on all of them, and then we play a series of rounds until the cards run out. We take a number of cards from the top of the deck and look at their sums. If the sum is between L and R, we win the round, and otherwise we lose. What is the maximum amount of rounds we can win during the game? In this example, our range is between 3 and 10. We can take 1 card off the top of the deck and the sum is equal to 2. Which is not in our range, so we lose the game. Then we can take the next 2 cards off the deck, and their sum is equal to 25, which is also not in our range, so we lose the game again. Take the top card off the deck, which is equal to 7, which is in our range, so we gain a point. Then we take the next 2 cards off of the deck, which sum to 3, which gets us another point. Finally, we take the last card, which is equal to 98, which is out of our range. So in total, we won 2 games, which is the most we can win in total. Our hint is to not use cards when they're not needed. For example, when 7 is the top card, we can take 3 cards which have a sum of 10 However, if we only select the top card, we are still in the range, and in our next game we select the top 2 cards and get a sum of 3. So this way we won 2 games using those 3 cards instead of 1. So let's try to greedily find the winning rounds. We go index by index, we try to find the shortest winning game that starts at that index. If we find one, we take those cards and we move on. If we don't, then we only take 1 card and then try to do the same at the next index. There are multiple ways to implement this, such as with a queue, or 2 pointers, or binary search. In my case, I used binary search. Let me show you how I implemented it. First, I calculated the prefix sums, which are the sum of the first I elements of the array for all values of I. I went index by index and used the lower bound function to find the first index of the prefix sums that was greater than or equal to the current prefix sum plus the left of our range. Then we check if that index exists, and we see if that range's sum is less than or equal to R. If it is, we found a winning game and we can move on to the next index after the winning game, or we can increment I and try again. And once we've done this for all indices, we found our answer for the whole deck of cards. Thanks for watching. I hope you guys enjoyed the video, and please leave feedback in the comments if you have any.